Vandana and you are watching 99.9 Engineering Station. So student, today we are going to take a numerical from the subject process calculation, and the question is, an absorption tower is used to absorb the carbon dioxide in an aqueous solution of monoethanol amine, that is MEA. The ideal gas mixture enters the tower at the 1000 meter cube per hour at 45 degrees Celsius and the 1 atm pressure. Okay, the carbon dioxide content in the mixture is 10% on the mole basis, and the outgoing gas contain only 5% of carbon dioxide. The MEA solution is introduced at the top of the tower at the rate of 500 kg per hour, and the dissolved carbon dioxide concentration at the entering solution is 0.15 mole per mole of MEA. So we have to find out the concentration of the dissolved carbon dioxide in the solution leaving the tower. So we have to find out the concentration of CO2 at the leaving of the tower. It means we have to find out the concentration of CO2 at here. Okay, so as we know that the absorption tower is the unit operation process. Absorption tower is used to separate the gas from with the help of any solvent. Okay, so here if we draw the schematic diagram according to the question, then we have that this is the absorption tower and we have two input. One input is for the gas mixture and one input for the solvent, which is monoethanol amine. Okay, so mixture of gases contain only 10% of carbon dioxide, which is given in the question, and the outgoing gas contain only 5% of carbon dioxide. Okay, so these are the data which is given, and the molar flow rate is given, that is mixture is 1000 meter cube per hour is the gas mixture input of flow rate of the gas mixture, and the solvent flow rate is 500 kg per hour. So according to the question, we have to find out the concentration of CO2. So what are the steps for solving this type of question? So if we find out according to this question, we have to find out first the volume, which is relevant to the used to calculate the number of moles of entering mixture. Okay, so first we have to find out the volume with the help of which law? That is Charles law. So what is the Charles law? Charles law is basically for a given mass of ideal gas, the volume of the gas is directly proportional to the absolute temperature at a given or at a constant pressure. So according to the Charles law, V is directly proportional to T at constant pressure. It means V upon T is directly is equal to constant. Okay, is equal to constant. So this is all about the Charles law. From here we calculate the volume, and then we are going to calculate the number of moles of entering mixture. So if we know all the number of moles of entering mixture, after that we calculate the number of moles of carbon dioxide in the inlet and outlet. Whenever we found the number of moles of entering mixture, and with the help of this second step, we are automatically calculate the number of moles of carbon dioxide in inlet or outlet gases. Okay, then we are going to solve or going to calculate the carbon dioxide absorbed in the, what is the quantity of carbon dioxide absorbed in the MEA, and then the next step for solution is that to calculate the total mole flow rate of the MEA solution, and after that the step is that is we have to calculate the concentration of the dissolved carbon dioxide in the solution, that is total carbon dioxide in the rich MEA solution. So these are the steps which we are going to follow to solve this numerical. Okay, so let's begin. So as we know that the 1 mole of ideal gas is equal to 22.4 liter at NTP. So using the Charles law, we are going to calculate the volume V2. According to the Charles law, I already explained that so that the equation become V1 upon T1 is equal to V2 upon T2. So the V1 and V2 is at the NTP condition. It means the volume is equal to 22.4 and the NTP temperature is 0 degree Celsius. It means it will be 273 Kelvin. Okay, and the given temperature for the absorption tower is 45 degrees Celsius. It means it will be a 316 Kelvin. So from here we got the V2, that is 26.1 liter per mole. So this is the volumetric flow rate of the gas, that is 26.1 liter per mole. Now we are going to calculate the number of moles of the entering gas, so that we will calculate the number of carbon dioxide present in the entering gas. So the number of moles is calculated by the total flow rate upon the volume, ideal gas, or number of moles. By the there are three formula for calculating the number of moles, which I already explained in my previous video, if you see in the my playlist. Okay, so the third formula, which is for calculating the number of mole, is molar flow rate, flow rate, that is flow rate upon the volumetric flow rate. So it will become 1000 upon 26.1 into 10 to power minus 3, because we are going to calculate into a kilomole. That's why we multiply with a 10 to power minus 3. So this number, from here we got the number of moles of entering gas mixture is 38.3 kilomole per hours. Okay, now the number of moles of carbon dioxide in the inlet gases. So in the question given that the carbon dioxide in the inlet gases is 10%. So we got the number of moles from here, and we simply multiply the present number of percentage of CO2 with the moles of the gas mixture. Then we get the number of moles of CO2 in the gas mixture. Okay, inlet gases. So 38.3 into 10 to into 0.1, that is mole fraction given in the question, that is it will become 3.83 kilomole per hours. Okay, now this we calculated that the number of moles of entering gases and the number of the moles of the carbon dioxide in the inlet gases. So if we separate both of them, then we get the number of moles free from the CO2. So if simply we separate the both of them, so we get the value of number of moles of CO2 free gases, that is 38.3 in minus 3.83, and it will become 34.47 kilomole per hours. Okay, now all the conditions, like this is our absorption tower and all the parameter in the inlet we calculated. Okay, now come to the outlet of the gases. The outlet gases, come to the outlets of the gases, that is outgoing gas contained. In the question we have given that given that the 5% of carbon dioxide present, okay, in the inlet outlet portion, in the outlet stream, and it means 95% free gases are present. Okay, so we calculated that from the above, that the 34.47 kilomole per hour is the number of moles of carbon dioxide free gases, and the free gases mole fraction is given here in the question. So therefore we calculate the number of moles of the outgoing gases from here, so by simply dividing it. So by dividing 34.47 upon 0.95, we get the 36.28 kilomole, which is the number of moles of outgoing gas mixture. Okay, then come to the what is the how much amount of the CO2 absorbed in the solvent, that is MEA. So now come to the, we calculate the inlet condition and we calculate the outlet conditions. Okay, now come to the solvent inlet conditions. Okay, so we have to calculate the carbon dioxide absorbed in the MEA solution. We simply calculate it by the number of moles entering in the tower and the number of moles out from the tower which is free from the CO2. So by subtracting both of them, we get the number of moles absorbed in the MEA solution. So by subtracting this number of moles entering in the gas and number of moles leaving the tower free from the carbon dioxide, we subtract them and then we get the value of 2.02 kilomoles of carbon dioxide absorbed in the MEA solution. So now we calculated the solvent conditions. Okay, now in the question given that the molar flow rate is of the MEA is 500 kg per hour. So if we calculate the molecular, if we know the molecular weight of MEA is 61. Okay, 61. So simply dividing it by the molecular weight, molar flow rate, we calculate flow rate and we get the molar flow rate, that is 8.2 kilomole per hour. So this is the molar flow rate of the 8.2 is the molar flow rate of the MEA solution. Now come to the last part of the question, that is we have to calculate the total concentration of the CO2 in the rich MEA solution. So for calculating that, we know that the 2.02 quantity kilomoles is absorbed in the solvent of CO2, and the condition is also given in the question that the 0.15 concentration is present in the entering of the MEA solution. So simply we multiply with the molar flow rate and we add it with the 2.02 content, and then we get the total number of carbon dioxide rich in 2.5. Okay, as you can see in the question, the as you can see in the question that the concentration of the CO2 at the entering condition is given at 0.15 mole per mole. Okay, so but our answer is come out from here that the total number of CO2 rich in MEA solution is 3.25 kilomole per hour. So we have to convert into a mole per mole condition. So simply we divide the molar flow rate with this total concentration and we get the solution or the total concentration of CO2, that is 0.396 kilomole per kilomole, and it is obtained by the dividing the 3.25 with the 8.2 kilomole per hours. So this is how we calculate all the points of the absorption tower and all the parameters of the absorption tower. So you can see that by simply noting down the step for calculating any numericals or a step for calculating the solving the numerical, it will become very simple to solve any type of questions, whether it is from the mass transfer, process calculation, CRE, mathematics and anything. So solve the numerical with the only by step. Okay, so if you understand all the numericals, all the concept behind the numericals, then please subscribe to my channel, share with your friend and like the videos, and please comment down in the comment section. Thank you and have a nice day.